for the people who are younger. And let me see if I have done something that is useful for you. So essentially I do some history and basics, and I then go to the stationary free boundary problems, then to the heat equation problems, that this is what I have been doing, and then I will do nonlinear diffusion and fractional. So the beginning is quite general, and the end is more or less what I do, which is the typical thing that people have to do. Okay, so the idea is that the concept of a stationary free boundary is relatively simple. You have a domain in Euclidean space, for instance, it can be manifold, and you have a variable or a number of variables representing physical substance or a mathematical entity. And then U is determined in the domain as a solution of a field equation, which is something that is derived in some way from physics or whatever application. And what we do is PDEs, but you don't necessarily do that. But we do PDEs. So essentially, you can do integral differential operators, but the idea will be the same. The most popular field equation is the Laplace equation. That is what we do all the time, but this is a model equation. The applications will tell you probably otherwise. And the catch of this game is that the domain is not a priori known. It's calculated along with you. And this is the point. You have to calculate a PDE solution, which is PDEs and analysis, and you have to calculate the movement of the boundary, which is differential geometry. And do they go together? And the idea is that both things do not go along very nicely, because the theory of PDEs, nonlinear PDEs, is based on estimates in functional spaces, and the theory of moving surfaces is based on characteristics. So it is not simple how to do the two things together. In any case, in order to move the free boundary, you don't have a solution of the problem with you and the domain completely determined, because otherwise there is no room for the domain to be where it has to be. You determine it because you say, I don't know what the domain is, but I will give another condition on the boundary. And only one of the possible boundaries will be the real thing. So it's a selection process by giving extra information to tell you that only this boundary will be good enough for you. And this overdetermined problem relies then on selecting very carefully the extra condition. I mean, there is one condition that is usually the typical thing, let's say Dirichlet condition, and another condition which is not a typical thing, like it's like a Neumann condition or velocity condition. So there are two conditions. They could be treated at the same level, but usually we take one as the first condition. For instance, we calculate with a trial boundary. With the first condition, you calculate the solution. And then you see that the second condition is wrong. So I say my boundary was wrong, and I move it until I find the solution that satisfies both. And the extra condition depends, it's called usually transition condition, and this is where the physics comes. You select the problems because they have good physics. Otherwise, the number of possible conditions is infinite, and none of them is very interesting. So this is the stationary problems. The evolution problems are a bit more complicated at the beginning, but they are more natural from the point of view of the applications, because many of these stationary states are the result of something that evolves in time very nicely. But essentially the same thing is that you come from the same general picture. Now the only thing is that the evolution is given, the domain at the beginning is given, because it's part of the initial data. And then it will begin moving to satisfy the extra condition on the boundary. So this is the idea, and this is what happens in, for instance, the Stefan problem, or the problems that we have been seeing about Alenkang or KPP in the limit. They will evolve in some way that they satisfy some other condition, and this is what determines the solution. So the typical free boundaries that appear in evolution processes are different from the stationary ones, because the beginning is predicted. And it's the evolution of the free boundary that is left to be calculated every time. Okay? So instead of calling them free boundary problems, some people say let's call them moving boundary problems. In the physical situations, it is not true that there is a sharp transition between the place where there is the substance and the domain that is moving. Usually there is something inside, which is the substance, and something outside, which is almost empty. But the transition is rather regular, and there is a transition zone. If there is a small parameter epsilon, as epsilon tends to 0, you get the free boundary problem. And this is what Professor Pertam has been doing this morning, telling you that if you go to a more detailed derivation of your application, you don't really have a free boundary. Now, let's be clear about elementary physics. If you go to the real derivation, you get atomic physics. So there's no free boundary and no continuous thing. But you don't want to be there because you are moving to 10 to the minus 10 meters. So you want to be in some place where the information is something that you can see in average. So you are averaging at a certain scale that is 10 to the minus 6, for instance, a micron, or 10 to the minus 3, a millimeter. So the point of the continuous models is that you don't want to see the physics at the atomic level. You want to see the physics that you are going to see around. And this is very important. Everything is a limit of something, but not very far, not very far. So the mathematics of these models are ideal models. The real models introduce variations, and this has to be clear. What happens is the free boundary models, once you calculate them, are very nice to look at. And they give you lots of information that if you want to go around with the smooth transitions, it's very difficult to get. So usually first you calculate an approximation, then you pass to the limit to see how nicely the thing is, and then sometimes you go like the last step going back to the epsilon next to 0 to see how the transition really was. So there are several levels of approximation. In any case, in free boundaries we consider there are sharp phase transitions because we are doing ideal mathematics. Okay? And then the derivatives will jump. And one of the points of the theory is having a mathematics that deals with discontinuous derivatives, and in fact the jump of the derivatives will be partly responsible for the movement of the free boundary. This is something that has been said before in these problems about the Stefan problems. There is not this, but this transition here. The derivative of u with respect to the normal is different from 0. And the velocity is proportional to the derivative of u with respect to the normal with a certain sign, okay, in the direction of the normal. So there is a problem with these discontinuities that you have to be careful about things. And now, in the typical case of, for instance, melting of ice and water, that is the Stefan problem, you have a manifold in several dimensions that moves. Now, since you say, let's do it brute force. Let's take a solution, move it, take a solution, move it, take a solution, move it, and then you find that usually discontinuities in the free boundary happen in finite time. So the brute force approach to these methods gives you very unstable geometry. So the problem that mathematicians want to solve is, do you have a free boundary really in your model? And it is a free boundary, which kind of object it is? It's a measure theoretical thing, it's a continuous thing. I mean, can you prove that it is somewhere, at least in some measure sense? Can you prove that it's a strange object, or will it be manifold? And can you find it numerically? Is the numerical approach useful to supply an existence proof? I will not insist in that because Professor Noceto has been doing that today. And these are typical things that you find in the internet about how a membrane sits over two bump obstacles. And this is an evolution of thermal release in plasmas modeled by the Barenblatt exclusion solutions for porous medium. So let me tell you some conclusions. In the typical tradition of the big people in mathematics, the free boundary problems takes the motivation from natural sciences or technology and poses a problem in pure mathematics. So the aims are different. And it is very complicated in these meetings to follow all the talks because there are so many different people. At least there are 4 kinds of people, plus the really crazy people, 5. Now, first kind that is not really crazy is the people who do a serious mathematical modeling and derive some mathematical model which is an ideal model. A mathematical model means that it is not very so close to reality that you have 25 equations with 135 parameters. This is not good in math. We are not going to do this here. If you go to talks in engineering where they do real problems, for instance in combustion, we have a very good group in combustion in Madrid, Professor Lin Yang. They have to write the 24 equations. In fact, sometimes they have to write 125. But this is not our job, because we want to do math. So essentially you want to have a simple mathematical model that is an equation with a free boundary, and they are simplified but relevant. So you know how to do it. And then you will see later if you want to work for some corporation or with engineers about the systems of many equations. Next, then you have a model, you develop a new branch of mathematics and contribute new tools based on analysis, PDEs, calculus of variations, and geometry. In some cases you use something else like ODEs or stochastic processes. But essentially the 4 guys in this room are analysis, PDEs, calculus of variations, and geometry. When I say analysis, I mean real analysis, harmonic analysis, functional analysis, which is 3 kinds of people. So 3, 4, 5, 6, it's too many people, it's too crowded. Next, then there are the people who do the job of making efficient simulations and develop rational numerical computation, which is different. The people who do the real simulations of complicated models have to do lots of incredible things to get a solution, and they don't have any convergence of nothing. And then in the basic models, the people do rational numerical computations based on analysis of what is going on. And this is very important to train yourself to see where are the difficulties. And fourth, you have to answer the motivating questions. So in fact, this leads back to applied mathematics. Many of these models, then when you have a model and you start a group of people working on that, you have to begin talking to someone who tells you that your application will be modified to do some other application to solve another interesting problem. And then you talk to people in fluid mechanics, physics, geometry, biology, finance. So if I look at this list, Benoit was in biology, and Ricardo was in fluid mechanics, just to assign them a niche. But in principle, mathematicians are mathematicians. You have to do your work. So the final mathematical result in mathematics is a combination of PDEs, calculus of variations, analysis, and differential geometry. And you have ODE, stochastic process, etc. And these 4 things will give you existence and regularity, which are the 2 great mathematical themes. And the machine is estimates. So any time that you want to do something in the conferences about mathematics, in pure mathematics like here, you do estimates. And we live by estimates, and we die by estimates. But we can estimate our estimate of dying. In that sense, the free boundary problems belongs to the extended family of nonlinear PDEs, because estimates is what PDEs has contributed to everybody else. So as people who are nonlinear PDE people, this is how I see things. Now other people will see different things. You make a list of problems, and depending on how you see the things, they will be interesting for you in different ways. For instance, free boundary problems with a stationary aspect, the obstacle problem is really the king of that. It's the beginning to train people. And there are many variants, 2 obstacles, P Laplacians, infinite Laplacians, 1 Laplacian, whatever. Then there is the dumb problem, which was very popular in the old times and trained many people in learning variational inequalities. And there are some other classical problems, but these ones, the 2 ones were the real model number 1 and model number 2. And then there are the problems with gradient-dependent transition conditions, free boundaries in contact problems, the Signorini problem, for instance, and free boundaries separating different phases. For instance, one of the phases has an elliptic condition equation, one of the phases has hyperbolic or parabolic conditions. How do you put the two phases together? And this is important. Now, in the case of moving free boundary problems, let me tell you that probably what was considered historically for us the king of moving boundary problems was the Stefan problem, which is this melting of ice in water. And then there is this Hill-Shaw problem that is the electrowetting in some sense. A very interesting problem. There was a time where people in Oxford were working non-stop on Hill-Shaw problem with some success, I think. And then I went there once and they told me, are you doing any Hill-Shaw? I said, no. And they say, are you staying how long? 1 month. Okay, do some Hill-Shaw. In fact, we did. So it was not so bad for me. We proved a very beautiful theorem which was based on complex analysis. Okay, next is mean curvature flows, which is very popular and difficult thing. Next is free boundary problems in combustion, which is a whole thing, where the main thing is taking the correct limit as epsilon tends to 0, because it's a problem of free boundaries about flames going around. And the flames are inside several thousand degrees, and outside it's cold. It's very important to do this separation. And there are free boundaries for fluids. Let's say fluids are water waves, cavitation, and this is a big industry now in the UK. There are flows in porous media. This is what I did a lot. Petroleum industry, ground flows. This is very important now for contamination. And there are free flows in evolution for elastic materials. Many people are now working on fracture. Then you want to see the evolution of the fracture zone, which is a free boundary. And there are free boundaries in finance. So let me tell you that the community of free boundaries is a big community. And this is a danger, because you maybe think that you have to talk to all of them. If you are very young, maybe you don't talk to many people, because otherwise you never concentrate on one problem. But this community has produced, over the years, a very long tradition of meeting and discussing problems. And there is these regular free boundary international congresses. The first one was happened in Durham, in UK, in 1970 something, I don't remember. And there is a list. There is one in Madrid, Toledo, Spain, in 1993. I was very young at the time. Last one was in Regensburg, in Germany. And there is a huge historical record of other events, which is where the real progress is being done every time.
Yes, no. I see you are still very young.
Oh, I see. Now, let me make some propaganda stunt. There are two things in which I participated. One of them is this 2011 program, Free Boundary Problems Theorem Applications, the MSRI in California. And it ran for several months. And it was very interesting as a training for younger people. We really enjoyed it a lot. I mean, the Bay Area is a beautiful place, but the point is that the training of younger people about this variety of things happened very nicely. I mean, you have to ask the experts about how well we did. So Henrik and Kuei Chang decided to present this application for the free boundary problems in Newton Institute. It will work for 6 months. And we are trying to see if we can do it again. Okay, so specific topics that people think about applications. Let me see, let me copy from one of these pages in the internet to see if the real thing that has not been edited by me looks like what I said before. Phase field models is very popular for some people because you replace the free boundary by a kind of function that determines how much of the transition you have been doing. And this is what you call the phase variable. And then there is a system. There is an equation for the real substance and another equation of how much you are in zone 1 or in zone 2. So it's a way of eliminating the free boundary that is very useful in the applications. And there is homogenization, which is a big business. And now, in fact, the mathematics among this incredible variety of problems is very interesting because it's the same thing all over. The mathematicians gave the whole field unity. It's a unique thing because it's still mathematics. So what you do is existence, uniqueness, regularity of solutions, regularity of interfaces, and asymptotic behavior. As Ricardo said, proving existence and regularity of solutions does not imply anything about the existence and regularity of free boundaries. And this is the important thing. You are doing two things at the same time. Proving existence and regularity of solutions and proving existence and regularity of free boundaries, which is nothing to do. So in the Congress in 2012, which was 2 years ago, they selected main speakers and I think they did a good job about concentrating on trends that were popular at the time. Well, usually you select a main speaker. He has been doing this interesting work for maybe 2-3 years at least. So it is not so trendy, but it's relatively new, right? And this is the list. Maybe one of the things that is very incredible as name is the mathematics of splashing, contributed by the famous John Ockendon. But there are free boundary problems in magnetohydrodynamics, which is relatively new, and it's incredibly important now. Combination of fluids with electromagnetic interactions. Look, so the electrowetting is a case, simple case, but in this field. And if you go to the mathematics, which is number one, you get global solvability or homogenization. And if you go to number three, which is computation, there is finite element techniques for the simulation of two-phase incompressible flows. And maybe you will understand every word and what they mean together. Because sometimes the titles are incredibly long, but for instance, computational approaches to coupling geometry and physics involving surface partial differential equations. Now, what is coupling geometry and physics is what we do all the time. The only news is that they say that on the surface there is a partial differential equation, not only a transition thing. Also you have it's like a bubble. Inside there is something, outside there is empty space, and on top of the bubble there is something moving around. So you can have a partial differential equation on the free boundary. Okay? Interesting. Okay, so let me go further and let me talk about some of the stationary problems. Now, since people in this audience have already contributed to the obstacle problem, I only have to say that it involves variational inequalities as a way to solve free boundaries. So the technology didn't start with the free boundary because it is too difficult. Unless you have a weak solution, you don't know what to do. And the weak solution is produced with a technique that was very popular in the 60s and 70s, which is variational inequalities, which was a new branch then of the calculus of variations. You solve the obstacle problem by minimizing an energy, an elastic energy, with the constraints, and you get a minimum, and the minimum will have a free boundary afterwards. So the point is variational inequalities was essentially optimal. Let me go through this because essentially this is what Ricardo said. The main example uses as a field energy to minimize the Dirichlet energy functional. Instead of the exponent 2, you put exponent p, and you get the p Laplacian energy. If instead of getting a power, you get a more general function, you get general variational minimization. And this is a whole history. The second ingredient is defining a functional space that includes the constraint. And the rest of it is calculus of variations that takes a long time to work on. And then one of the things that is very beautiful for the mathematics is that all of these things have to go back to PDEs. Calculus of variations has to go back to PDEs. This is a beautiful contribution of Euler and Lagrange. And Lagrange was an incredibly nice person, very insightful. And people, he lived in France at the time of Laplace, and he always complained that Laplace was not fair with him. We are fair with him because we know he was great. At the end of the day, there is one inequality, another inequality, and the product equal to zero. And this is called complementary condition, and people in PDEs begin to think that this is good life. We know what is going on. This has already something that Ricardo said. This is incredibly beautiful, the combination of two people looking with different glasses. People in calculus of variations and people in PDEs. People, engineers and people in PDEs like complementary principles. They want to know that one of them is true, but they have an inequality. And this forces a unique solution. If you are very good in calculus of variations, you know that. If you are not very good, you think that this is strange. So the complementary principle is incredibly strong method of proving solutions. And then the free boundary, once you know that there is a solution, you have to characterize the free boundary, and you have to prove that the free boundary is a nice surface, which is not true. And this is where the mathematicians are very good. You want to prove that it's a nice surface. So you put assumptions, like the obstacle is very concave, and the solution is the Laplacian equals f, and f is very good. And then, of course, there is a beautiful free boundary. But if you have one of these obstacles doing like that, it can touch several times, and the free boundary is a mess. Okay? So how do you eliminate these things? Oh, because in cases where you can have strange points, they are singular, and the measure is small. And this is a huge development in the 1980s, which is involving the group of people doing geometry and measure theory to free boundaries. And this is when I came into this picture, and I was about to quit, because I was at the time trying to train myself in elliptic equations, parabolic equations, calculus of variations, and some ODEs plus some probability. And somebody told me, listen, you don't know anything that is useful. You need to know measure theory and geometric methods. And I say, no, I will not. And well, I had a good advisor who told me, listen, forget it. You don't need it. I mean, you cannot do everything, but somebody else is doing it. So the people in measure theory tells you that singular points happen, but they are not many. They have a measure that is a Hausdorff measure that is positive on some lower dimension. And this is, for instance, one of the things that Luis Caffarelli knew very well, and since I was related to him, I was happy not to have to learn it, because he knew. And then one of the things you do is that the free boundary is very nice when it is transversal, but it can be terrible when it begins to do like this, like this, like this. So transversality, which is the discontinuity of the gradient, is your friend. If the gradient is flat, it is not your friend. You don't see the free boundary. So transversal points are the key to these things. And if the point is very transversal, then the error in the numerical method is very small. And then you get these beautiful slivers of situation of the free boundary based on the idea that the gradient was going down very quickly. So discontinuity is your friend. Okay, let me go to the heat equations. The heat equation is a simple thing that is only a PDE, so there is nothing to do. And the whole theory of the heat equation was based on thermal propagation and diffusion, and there are many people working on that, and the basic ideas is doing separation of variables and doing spectral theory or doing Gaussian representation. I will not talk about that. I will talk about nonlinear problems. Nonlinear PDEs were not considered until the 1960s, because there was no really strong mathematical theory to support them. Of course, the people in fluids knew all the time that Navier-Stokes is a nonlinear PDE system. So they knew something, but the whole theory began to be developed in earnest in the 1960s. And the typical parabolic equation that is the friend of the heat equation in this general context is something that has a certain, let me see if I can point, it is impossible, right? It has a certain nonlinearity I call AI that depends on U and gradient U, and has a certain convection and reaction which is B or something. So the main term is there, and AI is, for instance, identity. So you have di of gradient I, and this is the Laplacian. But if AI is a power of the gradient, then you get the P Laplacian. And there are many models of these parabolic equations with nonlinearities, and in fact, in the case where they do not degenerate, and they have no free boundaries, there is one of the typical books by Ladichenskaya, Solodnikov, and Uraltseva that is a good book. It's, in my opinion, a bit too long, but I will not complain. Okay, the typical nonlinear problems with free boundaries are 4. Stefan problem, Hill-Shaw problem, porous medium, and evolution P Laplacian. And we were trained in learning these 4 in the old times. And then if you want to do reaction with nonlinear, then this is a different field that is blow-up equations, and this is the Fujita model. So there are models of nonlinear heat equations that do not lead to free boundaries normally. And the fluid flow models, Navier-Stokes and Euler systems, they have lots of free boundaries because one of the media is water that obeys Navier-Stokes, and the other one can be considered empty. So there is a surface. And then you get gravity waves or water waves, whatever. So Navier-Stokes contributes lots of free boundaries. And there is another beautiful nonlinear heat equation, which is the Ricci flow, which is very related to movement by curvature. So not very far from Ricci flow, you get people in geometry working on free boundaries. So let me go to the Stefan problem. The Stefan problem is simply, as I promised to remember here, in the two-phase case, one part is water and evolves according to heat equation. Another part is ice and evolves according to heat equation, but the diffusivities are very different, K1 and K2. K2 is practically 0. So there is a difference between in the media. So you have to separate media 1, media 2, and is there a nice free boundary between ice and water? What happens in nature? Glaciers have a smooth free boundary. Glaciers intruding into the water in North Atlantic? No. So do you have a nice free boundary for this mixture? Probably not. Do we have free boundaries for the Stefan problem that are very nice? Yes, unless you consider the singular points. So who is the responsible for explaining to you singular points? Probably Luis Caffarelli. So this is the whole story about the thing. This is a very interesting problem about how to move the media obeying simple equations. Simple, I call simple as advanced mathematics, everything that is related to elliptic solvers or parabolic solvers with no degeneracy. But the problem is the free boundary, and the free boundary is not very, very nice. So how do you prove this? Okay, if you want to get a simpler model, in one phase you get, instead of heat equation, Laplacian equals 0 on U larger than 0, which is more or less like the water. And on the part of the ice, 0. And the movement is V equals proportional to the gradient of U. So this is the typical thing, so where you have a certain domain, omega t, with a certain gradient U equals 0, and then it moves according to the derivative of U with respect to n at the free boundary in the direction of the normal. And you say, maybe this doesn't make a sense because you are putting as first condition U equals 0, for instance. But then you put U equals 1 here, and this is the fixed boundary. And for instance, you have this, and now it moves, it moves, it moves. Okay? So this is a possibility. So you of course, you need in the problem something that is not 0. Once you start it, you get Hill-Shaw. Now, Hill-Shaw is beautiful because the equation is usually in 2 dimensions the Laplacian. So it's the real part of an analytic function. And you can do complex variables. And this is a wonderful life. But I didn't do that. I did porous medium equations. And porous medium is very interesting. because this ideology that first you calculate the solution and then you discuss if there is free boundary or not is very simple when you think about this thing and you put u equals 0 equals u0 of x. This is a model of heat propagation at high temperatures, for instance, the plasma Bremsstrahlung effect for plasmas. And then this is u0 is, for instance, continuous, non-negative, and the support of u0 is compact. Okay, so essentially u0 is something like this, and then you want to move it, and what happens is that for every t larger than 0, omega t, which is the set of the points x where uxt is positive, is contained in a compact kT. So it begins moving and moving. Now, do you need to construct a solution with geometry to know that this porous medium flow has a solution? No, sir, because in the case of the weak ideology, you do this thing, dx dt, and then you get the weak solution. And you don't need any differentiability. You don't need continuity. You only need integrability. Okay? So the only thing you need to get the solution is that u and um have to be L1 log in space-time. Okay? No, so do you prove that there is a solution that has a free boundary? It doesn't make any sense at the beginning. You have to prove first existence of a solution, second, uniqueness of a solution, third, continuity of the solution, and then the existence of omega t is true. But is omega t compact? Then you have to prove super solutions which look like viscosity approach. To prove that in fact there are explicit examples that you can construct that are on top of your solution. And they are balls that, big balls that propagate with finite speed. So your ball is below, in maximum principle, there is a free boundary. So proving that the free boundary is there is relatively simple. The main difficulty is proving that there exists delta omega t, gamma t, which is a C-infinity manifold. Can you prove it? In fact, we are working with Herbert Koch and one of his students in proving that under minimal assumptions on the data. And this is 30 years later. So let me just recall for the people who want to see the difference between slow diffusion and fast diffusion and normal diffusion. If then in the porous medium you want to see a free boundary, you have to put MO larger than 1 to get the free boundary. If M is equals 1, you get the heat equation, no free boundary. If M is less than 1, you have a fast diffusion, no free boundary. So only for M larger than 1, there is a free boundary. And the point, one of the main problems for mathematicians was to prove the infinite regularity of the solutions. Of course, there could be, for some geometry, singular points. And we can describe some of the singular points, which are called focusing points, but the whole description is open. So let me tell you the last thing, because I promise that at the end of this presentation of different styles, interest, communities, and orientations, I will give you a new problem that I'm working on. And since some other people have mentioned it, let me derive for you the nonlinear diffusion model that is at the same time non-local. And the idea is that, let me derive it. You are too tired, right? Okay, let's go for it. Okay. Okay. No, I'm just relaxing a bit because my life is so intense. Okay, let's start again. Let's start again. This is a new game, right? I will derive an equation, I will tell you what to do with it. So this is a model like any other model. It's very popular since, let's say, 7 years ago, which we call non-local diffusion, which in practice is fractional. For mathematicians, is fractional ablations. Let me go for it. You start in my derivation. So you will ask me, why do you start with a derivation? Oh, because England is a place where deriving physical models is appreciated. So if you are in France, you think about assumptions, les actions. If you are in England, you think about derivations. If you are in Spain, I don't know, you think about going to the beach. Okay, so the first equation is the basic conservation law for the density U of a certain substance, like bacteria. Okay. Next thing is that this conservation law, which you already know, is driven by a certain velocity. And the velocity is, in our case, a gradient of a certain potential. The potential is usually in the physics the pressure. But in any case, this is a potential flow. We are assuming potential flow, which in many cases is justified by the statistical mechanical approach. There is a potential. Once you assume that there is a potential, you say, I have an equation with U and V, but this gradient P, I have to say something about the equation for P. And then there are many ways of writing the second equation as a system, but in my case, I will relate directly P with U by what I call a state law. For instance, in gases, or pressure is a power of density. But if you put P equals a function of U, then a very simple derivation tells you that, let me tell you how I do it. Ut plus this is it. This is the derivation of porous medium. For gases that evolve according to this V equals gradient P, which is Darcy law. So this was porous medium. Let's go to do something else. If you go back to the derivation, people began complaining that in some applications of porous medium, which were not the original applications, it is not true that P is a function of U, because this will say that the pressure that moves the fluid is instantaneously originated at the same point, and there is no influence in the pressure of of the rest of the population. Now, if the pressure that moves bacteria is put into this equation, it's not realistic to say that the pressure is given only by the number of bacteria present at this point. The rest of the population around are getting some kind of chemical interaction that drives the whole population to do something. And this is chemotaxis. And there are many applications where the interaction between one place and another place is felt in the building of a certain pressure that drives the fluid. So, make it short. The interaction will be that P is a risk potential of U. It is an integral of U with respect to a certain kernel, and the kernel is written there, is one of distance to some power. And that's it. And this is what we call a Levy interaction in probability. You write then the equation, and then the equation is not anymore the original equation, because in fact, since P is this kernel applied to U, this thing is this thing. And this is ugly looking thing, but it's not so ugly looking, just to start it. This is the project that I started with Luis Caffarelli in 2007, and we produced a theory of existence and asymptotic behavior and regularity, and we still don't know what is the uniqueness of this problem, which is amazing. So let me just tell you, because we have been talking about this fractional Laplacian, maybe people want to know, just to start this week in style, what is the fractional Laplacian? Fractional Laplacian can be defined by using Fourier series as an interpolation. Remember that what the operator that is positive is the minus Laplacian, and this is a positive operator in interpolation. So you have to put a minus in all the definitions, right? It's very cumbersome, but it works. So you define Fourier series, and it's very easy. Instead of having symbol xi to the 2s, to the 2, you have symbol xi to the 2s, interpolation. Now, you want to represent it, eliminating Fourier series to do integrals. And then the corresponding operator that corresponds to this symbol that is degenerate is a singular operator that has a certain singularity downstairs. In order to eliminate the singularity downstairs that is not integrable, you cannot do a pseudo-differential operator in the typical sense. You have to do this kind of complementation upstairs that allows to eliminate the singularity. If u, for instance, is a regular function, upstairs there is a term x minus y, for instance, to the power 1, and it cancels the 2s downstairs. So this is the way to define a singular operator that allows to represent this process. But there are other ways, that is using discretization and making transition probabilities where the interaction between one point and another point is represented by a discretization of that kernel. So you can do a discrete random process based on these matrices of influence between one point and another point. If you do that, in the end, your process will have an operator that is the generator based on these stochastic movements with this transition process. And then what is beautiful is the thing that we do, let's say what we call Caffarelli and friends. It is something that came from geometry. The best thing for many calculations in PDEs to represent the fractional Laplacian, put s equals 1/2, so it's minus Laplacian 1/2, is doing this. Take your space, omega, take an initial datum, u0, expand it to a certain function that does Laplacian of u0, let me eliminate the naught, u of x. The Laplacian of uxc equals 0. But this function depends on a new variable, the external variable. In some sense, you invent an extra dimension where you are solving the heat equation. Oh, sorry, the Laplace equation. Now, if you have a function and you replace this function, remember that capital U on the bottom has to be equals U. And then I take a function, I invent a new dimension, I solve the heat, the elliptic equation, and then what is the Laplacian? The minus Laplacian 1/2 of U is the derivative of gradient u with respect to the normal with a certain constant. This is it. So you eliminate completely the fractional Laplacian. The only thing you have to do is invent a new dimension, and in the new dimension you solve the Laplace equation and you get the Neumann data. So the Laplacian 1/2 is the operator that goes from Dirichlet data to Neumann data with respect to the canonical elliptic extension. Is this easy? Yeah. Any calculation that you have to do about some minus Laplacian of u 1/2, you replace it by derivative capital U with respect to the normal, with a certain constant. And you work in one dimension more and you do your integrals. All the estimates will be true there, and you will do these beautiful calculations. And how do you do all of these possible interpretations in Areno? It's okay. They have been proved to be the same. How do you do it in a bounded domain? Oh, in a bounded domain, probabilities that influence people very far away have a problem with the boundary. Because even if you put a boundary and you are talking by internet, you go over the boundary to talk to the people outside. So the influence of the boundary conditions tells you that these definitions that I have been writing of fractional ablation are not the same. So which one do you use? We are working on that. Part of the work of fractional ablation in bounded domains is trying to know how different are the solutions and which one is the definition that you want to use. Part of the work has been done by people in probability, but the people in probability don't have free boundaries, so we have to do the work again, analytic ways, to do free boundaries. And let me tell you that there is another, this is the program that we want to develop for this thing. You study the regularity of the solutions, you study the equation and regularity of the free boundary, asymptotic behavior, or you study the problems in bounded domains, you decide conditions for uniqueness, for comparison, you do a performing numerical code, and you consider different non-local, non-linear diffusion problems. And then you go to the people in stochastic particle models. How much of this problem is already done and after 7 years? Let's say 30% or less. And then you want to do some other models. This is the second model that we have been using that is simpler, because in the other model we have put this Laplacian in a very strange way. ut plus divergence of u gradient of minus Laplacian minus s of u, which is very strange. But it is the physical model. In some other models, the minus Laplacian appears as a simpler modification of the heat equation. We didn't do it at the beginning because we spent 2 years chasing applications. But in any case, now that we have the applications, we have been doing the analysis of this second model, which is called probably the normal fractional porous medium equation. And there are a series of papers that you can look at in internet with my group in Madrid, the Pablo Quiroz, Rodriguez, and myself. And there are more collaborations working on that. Now, there is a point of the second model. Bad news for you. There's no free boundary. So it's a very nice theory about nonlinear semigroups using fractional operators, having interest in analytic behavior, behavior at infinity, asymptotics, wherever, but there is no free boundaries. So I wrote a survey that will be available on my webpage. I will have to upload it now. It's going to appear in DCDS. And a number of models are investigated by different authors. So let me write on the blackboard the different model with which I am telling you what my students here present and myself are interested now. And this is something that was motivated by work in France by Régis Monod, who is working on dislocations. So one of the models I was using is this one, right? And another model is okay, this has free boundaries. This has no free boundaries. How do you make a connection between them? Okay, there is a possibility that is put here, u to the m gradient minus gradient s of u equals 0. And when m equals 1, you get model 2. And when m equals 0, you get model, no, m equals 1, you get model 1. When m equals 0, you get model 2. M equals 0, you get model 2. Oh, you have to put something here. Yeah. Okay. Okay. Oh yeah, with different m. Okay. Let's put m minus 1. So it's m1, m1. But there is another way. So this is model 3, model 4. The idea is that, do they interpolate? This model is very interesting. If m is equal or larger than 2, there is a free boundary. If m is less than 2, there is no free boundary. And this is a note in Conrandu online this week. And my students are Diana Stang and Felix Teso. And there is work that is being done in Imperial College by Juan, here present also, Imperial College, on explicit solutions. So with this note of collaboration with the younger authors here present in the audience, I thank you for your attention. So the idea is that you should tell me your opinions and your criticism and your complaints about if the things that you will be seeing around fit in more or less with this picture. It's just a rough picture, but I hope it will be of some use for you, right?
Thank you very much for your beautiful talk. So I think it's time for wine reception. Suppose it's a lady outside. Let's thank our speakers today.